Okay, optional starter. If you want to skip this, that's fine. But I'll put the questions up now. So this is stuff we've done on probability before. Okay, so question 1, what are mutually exclusive events? Mutually exclusive events are events where both can't happen at the same time. So an example of that would be it raining and it not raining. It can't be doing both of them at the same time. Question 2, getting the 7:15 AM bus to school tomorrow, getting the 7:15 AM train to school tomorrow, mutually exclusive events. Well, you can't get on a bus, on a train, so that would be mutually exclusive. Are eating your tea at 7 PM tomorrow night and watching the telly at 7 PM tomorrow night mutually exclusive? First thought it might be that they are, but actually you could be eating your tea while watching telly, so they're not mutually exclusive. Okay, and last one, you have a wardrobe consisting of yellow, red and blue shirts. If the probability of picking a red shirt is 0.4 and the probability of getting a yellow is 0.5, what is the probability of getting a blue? Well, if your wardrobe is just yellow, red and blue, then the probability of getting one of those colours has got to be 1, because that's a certain thing. So we know that 0.4 plus 0.5 plus whatever the probability of blue is 1. So that means blue has got to be 0.1 for that to work. Okay, so what we're looking at today is, this kind of ties in some stuff we did before. We're looking at estimating probabilities, so using kind of trial data to work out an estimated probability, and we're going to see what relative frequency is. So relative frequency is basically a measure of how often something happens. So if the relative frequency is 1, then it happens every time. If the relative frequency is 0, then it never happens. And the calculation we do to work out relative frequency is the same as the experimental probability. So by working out the relative frequency, what you are working out is the experimental probability. They're kind of the same thing, they're just subtly different. The probability is how likely something is to happen. The relative frequency is how often it does happen. So while the number is the same, the relative frequency number is the same as the probability number. What they are is kind of subtly different. But if you can work out the relative frequency, you've also got the experimental probability. The number is the same. So let's have a look at an example. So we've got a table here of cars in the school car park. So we've got how many cars are in the car park, what is the probability of choosing a silver car. So how many cars are in the car park, we look at how many of each colour there are. So we've got 2 red, 4 black and 6 silver, so we've got 12 altogether. What is the probability of choosing a silver car? Well, 6 out of the 12 are silver, so that means 6 out of 12 is our probability of choosing a silver one. So that is 1/2. So as well as being the experimental probability, which is what the questions ask for, this is also the relative frequency. So the experimental probability is 1/2, so that's how likely it is to pick a silver car. But also this is what proportion, so if 1 is every car is silver, and 0 is no cars are silver, 1/2 is also the proportion of cars that are silver, so that's what the relative frequency is. It's how frequent it is relative to all of them. So we work that out by doing the number of times the event happened, so in this case that is number of times silver, and the total number of events, so that is total cars. So you can see we work this out in exactly the same way as the experimental probability. So let's have another look at another one. So if we've done the silver already. So again, just working through, it's the same method for the red and the black. So we've got 2 red cars, so we've got 2 out of 12, which is 1/6. And the black cars, we've got 4 of them, so that's 4 out of 12, which is 1/3. Other, we've got no other cars, so that's 0 out of 12, which is 0. So we've got our relative frequencies for the other. So with this, we can see a bit of a problem here. So we've got 0 other cars. So if you were to try and use this experimental frequency as a probability, what you would have is you would be operating on the assumption that there is no other cars. There is only silver, red and black cars. Because with this, the probability is 0. So this is just because we've got a very small sample size. We've only got 12 cars. So quite often with questions like this, if the number of trials is very small, so if you're doing dice rolls and there's maybe 3 dice rolls, If the number's not very high, it's not going to reflect the actual probabilities. So you need to have the higher the number, the more accurately it reflects the real probability. So if it was a survey of 1,000 cars, you'd get a much more accurate representation. So just a sort of summary slide. So the relative frequency is an estimate of the probability based on some experimental data. So in the case before, it was cars in a car park. So it predicts how likely it is to happen based on an experiment. Yeah, so we'll see an example of that. So there's an activity here you can do. This is optional, so if you don't want to do it, that is fine. We've got a website link here, which is a dice rolling one. So I've set it up so where it's got num equals 24, that means you've got 24 dice. What this does is it simulates rolling 24 dice, and then we've got a table here, so this is when I did it. I've then counted up how many of each number I got to see if it's what we would expect. So on a dice roll, in theory you expect that all of the numbers are equally likely. But we can see here, when I did it, I got 7 ones, and I only got 1 5. So it doesn't look that fair. But the problem here is that what's happened, because I've only done it 24 times, when there's 6 possible outcomes, that isn't that high. So I'd expect that for each one you'd have a sixth of 24 would be each one, so you'd expect to have 4 of each. But because I only rolled it 24 times, it's not been that accurate. So this is what I was saying before, about if the number of trials is bigger, we get a more accurate representation. So if instead of doing it 24 times, I'd done it 24,000 times, we would get a much more accurate representation of the probabilities. So small number of trials gives a less accurate probability. So that's something to bear in mind. Quite often with these questions, it'll say, why is this not necessarily true? If they've said it's a biased coin or dice, it's quite often because they've done a small number of trials. Okay, so let's have a think. What would we expect if we rolled the dice 100 times then? So, if we rolled a dice 100 times, each time we've got a 6th chance of getting each of the outcomes. So, if we roll it 100 times, we expect a 6th of 100 to be each one. So, to work out how many of each we expect to get, we have the number of trials and we multiply it by the probability of each one. So each one we have a probability of 6th. So to work out the probability of each one, it's a 6th. How many of each we're going to get, it would be a 6th times the number of trials. So I've got 100 over 6, so that's 16.6 recurring. So with this, we've got we'd expect to get 16 or 17 of each one. And getting back to what we did before, because the number of trials isn't that many, 100 is not that many when you've got 6 outcomes, you would expect some variation in there. So although we expect to get 16 or 17 for each, it won't necessarily be exactly that, it'll just be around that. But this is why it's called an estimate, because it's not exact. So the formula we're going to use to do this, the expected number of successes, so in this case successes just means kind of the outcome you're interested in. So if it was expected number of 6s, you would use the probability of getting a 6 times by the total number of trials you do. So comparing this to our previous example where we did 100 dice rolls, our number of trials was 100, probability of getting a 6 on each one was a 6th, so we did a 6th times 100 and we got 16.6 recurring. So with this is the formula we're using. So relating this to what we looked at earlier though, so this is using with a dice roll you've got an exact probability of a 6th. You can sort of work that out by looking at dice. You can see you've got 6 outcomes and they're all equally likely. If it's something less clear, so the number of cars, you might use the relative frequency, so like an experimental probability. So you'd work out the relative frequency and use that. So in general, if possible, you would prefer to use a probability like this, so like a coin toss or a dice roll, where you can work out what the probability is by looking at it. If you don't have access to that, you would use an experimental probability, which we calculate by doing the number of successes divided by the total. So we saw that in the earlier slide. So this is experimental, and this top one is kind of non-experimental, we'll say. Okay, so now just have a quick think about this. So pause the video, check your understanding on this. So how many times you'd expect to roll, we'll say roll a 6 on a dice roll. So if you do 60 rolls, how many would you expect to be a 6? 150, 290. What would we expect? How many 6s would we expect to get? Okay, so using our formula, expected 6s. So that is probability of 6 times by number of trials, so number of rolls. So expected number of 6s, so we do probability of getting a 6, which is a sixth. The number of rolls we did was 60. So we've got a sixth times 60, which is 10. So our expected number of 6s is 10. For 150, same formula, probability of getting a 6 times by the number of rolls. So I'll just put 6s equals, so it's a sixth times by 150. So that would give me 25. So I'd expect to get 25. Obviously, because it's a random thing, it would be a bit above or a bit below. But I'd expect to get around 25. If it was massively different from that, you could say it was probably a biased die. So if you rolled just 1, you might say that's biased. If you rolled 60, you might think it was a biased dice as well. So the last one, 290. So again, number of 6s. We've got a sixth times 290. So we do 290 divided by 6. So that would be 48.3 recurring, I think. So yeah, so with this one, we've got 48.3 recurring. Although this looks like you wouldn't expect to get 48.3, you'd expect to get either 48 or 49. In maths, we leave our estimates exact. So like this, even though we know that we can't get 48, we'd leave our estimate in this form. We wouldn't round it up or down. So you can get decimal expectations, even though obviously you can't get 0.3 of a 6. Okay, so now an example. If you want to pause and have a go at this yourself, you can do. If you'd rather watch this one as me going through it, that is fine as well. So we're told the probability of rolling 2 dice together and getting 2 6s is 1 out of 36. And we saw how to do that a few lessons ago with the sample space diagrams. If I throw 2 dice together 108 times, how many double 6s would I expect to get? So we're going to write out our formula. So expected double 6s. So this is how many times would I expect to get a double 6. And we've got probability of double 6 times by number of trials. So in this case, how many times I'm rolling the 2 dice. So that would be 108. So expected number of double 6s. So the probability of double 6 we're told is 1/36th. And we're timesing that by 108 because that is the number of trials. So we're doing 108 divided by 36. So that would be 3. So if we roll 2 dice together 108 times, we'd expect to do that 3 times. So you can see it's fairly unlikely. You'd have to roll the dice a lot of times in order to get not that many double 6s. So yeah, fairly straightforward. You are basically looking at the probability, multiplying that by the number of trials. So this one's a little bit different. We're going to use the same formula, but we're actually looking for a different thing. So the probability of rolling, if you want to pause by the way and have a go at this, you can do. Probability of rolling 2 dice is, and getting a total of 7 is 1/6. So again, you can work this out from a sample space diagram. If I want to throw a total of 7 on 2 dice, how many times would I expect to throw the dice? So this one's a little bit different. So we've got expected number equals probability, I'll put expected number of success. So probability of success times by number of trials. So reading the question carefully, we're looking at how many times would I expect to throw the dice. So actually what we're looking for is how many trials we're expecting to do. So how many times am I expected to do it in total? So let's substitute in what we do know. So if we want to throw a total of 7, so that's just doing that one time, our expected number of success then is 1. So we're interested in how long it takes us to get 1 success. Our probability of success is a sixth, and it's our number of trials that we're interested in. So that is our unknown, the number of times we're going to have to throw the dice. I'll just put number of trials. So we've got 1 equals a sixth times the number of trials. So if we're just trying to get the number of trials on its own, we can times both sides by 6. So that gives us 6 equals number of trials. And this is still an expected number of trials. So because it's rolling a dice, it does have an element of randomness. So it won't be exact. But 6 is our expected number of trials. I'll put expected underneath. So this kind of makes sense. If we've got a probability of a sixth, it makes sense that to get the outcome we'd have to roll the dice 6 times. So this is a little bit different because we're rearranging the formula, but a similar idea. We're using the same formula that we're just having to rearrange to get what we're interested in. So worth being careful on these ones. Check that you are looking for, whether you're looking for the expected number of successes or the expected number of trials. So with this one we're looking for the expected number of trials. Okay, so one to test your understanding. So if you want to pause the video and have a go at this before starting the task, you can do. Again, if you want to just watch it as an extra example, that is fine. So if I have a coin in a dice, what is the probability of getting a heads and rolling a 5? So that's part A. So let's do part A. So we've got heads and tails, and that is a half for each. And then rolling a 5. So there's only 1 5 on a dice, so that is a sixth. And it's 5 sixths of not 5. So we could do 6 branches, but we'll save ourselves some work and just do 5 and not 5. If we roll the tails, we've got 5, not 5, and the probabilities are the same. So that'll be 5 sixths. Okay, so we've got our probability tree. What is the probability of getting a heads and rolling a 5? So we get down the heads branch, down the 5 branch. So we've got 1/2 times 1 sixth, which is 1/12. So our probability of getting a heads then a 5 is 1/12. Oh, sorry, it doesn't say about the order, so we could also... anyway, sorry, that wouldn't matter. Yeah, so we've got a heads and a 5, so that is 1/12. So if I toss a coin and roll the dice 342 times, how many times would I expect to get a heads and a 5 together? So we've worked out our probability of getting a heads and a 5. What we need to do now is use our formula. So we've got expected success equals probability of success times by, I'll just put trials, number of trials. So we're told we've got 342 trials. We've worked out our probability of success is a 12th. So we've got 1/12 times by 342. So now we need to do 342 divided by 12 to work out our answer. So we work that out as 28.5. So our expected number of successes is 28.5. So again, we've got a decimal one, but that's completely fine. So with this, you can go ahead and start the task now. If you have any questions, feel free to email. It is a bit of an unusual topic, but like I say, if you have any questions, feel free to email.